Hello and welcome to Oxidation Numbers. So, to start the show, I'm going to give you a brief overview on oxidation numbers and what they are, so that when you move on to the other presenters, you'll have the basics down. So, what are oxidation numbers? As unrelated as this looks, it's actually a fundamental part of oxidation numbers. It is, of course, an oil rig. Now, oil rig is a very handy acronym to remember the definitions of oxidation and reduction. Loss and gain refers to the movement of electrons from atoms. When an atom is oxidized, it loses electrons and its oxidation number increases. When an atom is reduced, it gains electrons and its oxidation number decreases. An oxidation number is simply a way of keeping track of how many electrons a specific atom gains or loses in a reaction. They help to visualize the transfer of electrons, most notably in a redox reaction. The history of oxidation numbers is fairly simple, but they really are an integral part of chemistry, as they are such a key jumping off point for many discoveries. As with many scientific discoveries of the time, oxidation was posited to disprove another idea. Lavoisier was trying to disprove the widely accepted idea that any flammable substance had an element of fire in it, dubbed phlogiston. The idea was posited mainly by German scientist Georg Ernst Stahl in the early 1700s. In an experiment, he discovered that when flammable air, which we now know as hydrogen, was oxidized, or reacted with oxygen, it created water. He concluded that water was not an element but a compound of oxygen and the flammable air. This led to the idea of oxidation and disproved phlogiston, so Lavoisier was happy. The term oxidation has since been generalized to imply the loss of electrons. The next step in the history was when chemists in the early 1800s, such as Michael Faraday and Humphrey Davy, were doing reactions involving electricity, resulting in the idea of charged particles moving in a reaction. These charged particles are of course electrons, but at the time they hadn't been discovered. In 1897, J.J. Thomson discovered the electron, and the idea of those charged particles were linked up by the work of many scientists, including Gilbert N. Lewis, whose work posited the idea of electron pairs making bonds and helping finalize the definition of oxidation numbers. Which leads us to the modern day UPAC standard definition, which is an oxidation number gives the degree of oxidation of an atom in terms of counting electrons. The higher the oxidation number of a given atom, the greater its degree of oxidation.
The word redox comes from the mechanism of the reaction, in which one metal ion is reduced, whilst the other metal ion is oxidized. Reduction is the gain of electrons, whilst oxidation is the loss of electrons. A reducing agent gives electrons to something else, whilst an oxidizing agent removes electrons from something else. If we take a look at the reaction between zinc metal and aqueous copper 2 ions, we can see that the zinc metal acts as an oxidizing agent, obtaining a charge of +2, whilst the copper 2 ions are reduced into copper metal. We can say that the net change in this reaction is 2 electrons, lost by zinc and acquired by copper. Half equations can be used to visualize the movement of electrons in a redox reaction. When magnesium burns in air, it gains oxygen and is oxidized to form magnesium oxide. We show this reaction with the following equation. The following half equations would be for this reaction. It is important to remember that the electrons are not free in the reaction mixture. It is just used to visualize the movement of electrons and better identify the reducing agents and the oxidizing agents. Half equations also helps identify where these reactions takes place if it was done under electrolysis. Reduction takes place at the cathode, whilst oxidation takes place at the anode. For the reaction of magnesium burning in chlorine, using the half equations, we can identify that the magnesium being oxidized takes place at the anode, whilst chlorine being reduced takes place at the cathode. If we add these half equations together, we get the full equation, which is magnesium, and chlorine makes magnesium chloride.
I'm going to talk you through the trends of oxidation state, starting with group 1 alkaline metals. Ignore hydrogen for now because it's the special one. Group 1 metals each have one valence electron and form ionic bonds with a +1 oxidation state. Next, alkaline earth metals have a +2 state since they are losing 2 electrons. Group 6 elements such as oxygen are good oxidizing agents with -2 state, while group 5 has a -3 state. In group 7, the halogens are 1 electron short of the full shell, typically resulting in a -1 state. Finally, hydrogen, the unique one, it has 1 electron and can act as either positive or negative charge. For example, in lithium hydride, hydrogen is -1 and the overall charge is neutral, is 0, while in hydroxide OH- is +1 for hydrogen and makes an overall charge of -1. Now let's move on to d block elements or transition metals with variable oxidation states as shown in the table I created. However, scandium and zinc found at the end of the series only have one oxidation state. This is because transition metals seek to achieve a noble gas configuration for stability. For example, two most stable oxidation states for manganese are manganese 2+ with a configuration of Ar3d5 and manganese 7+ with a configuration of Ar. In D block elements, oxidation state differ by 1 unit, whereas P block elements they differ by 2, and the key contrast is in the stability of oxidation states. In P block elements, lower oxidation states become more stable than the group due to the inner pair effects. For example, Bi with a +3 is more stable than with 5. On the other hand, in D block elements, higher oxidation states tend to be more stable as you move down the group. Examples are shown in the slides. And the reason for this is because 3D orbitals are smaller, more compact, and closer to the nucleus than 4D and 5D orbitals, leading to greater nuclear attraction. As a result, electrons in heavier elements are more free to participate in chemical bonding, making higher oxidation states more stable.
So one thing that we like to talk about quite a lot when we're thinking about oxidation numbers is the D block transition metals. Obviously, they're found in the D block of the periodic table, and they have variable oxidation states. So unlike other main group elements, such as helium, oxygen, or hydrogen, they don't just follow one rule or have one oxidation state. For example, manganese is stable in 5 different oxidation states, ranging from +2 to +7. The reason they have variable oxidation states can be easily explained using the electronic configuration. So we'll just take a look at iron as an example. It has electrons in the S, the 4s subshell, and the 3d subshell. And the energy between these is so similar that it would be just as easy for me to take an electron out of the 4s subshell as it would for the 3d subshell, which allows a range of oxidation states to form in bonding. One of the reasons we like oxidation states being varied in transition metals is because it makes them really good catalysts. But it isn't just humans that rely on these oxidation states of transition metals. This is a bacteria called Azotobacter. It likes to keep our soil nice and healthy and fertile in a redox reaction between nitrogen and vanadium, in which nitrogen is reduced and vanadium is oxidized from +2 to +4 state. These are called C-squirts. They acquire vanadium in the +2 oxidation state from seawater, which they then use for defense against bacterial infections. Not only does the vanadium help defend them against bacterial infections, but they can also store it on their blood cells, which they use to create vanadium-binding proteins called vanabins, which help them with growth and repair. These are in the +3 and +4 oxidation states.
Moving on to a more advanced part of oxidation numbers is its involvement in spectroscopy. Now, we are already aware of the main three techniques, proton and carbon-13 NMR, infrared spectroscopy and mass spectrometry. Zanes is another type of spectroscopy and allows for the determination of oxidation numbers. It stands for X-ray absorption near edge structure. Similar to mass spec, Zanes uses ionization to extract data from different species. The ionization chambers and therefore spectra are affected by voltage, gas used, and method of ionization. However, we will focus on the voltage. An article relating to lithium iron sulfide cathodes found in their results that sulfide was oxidized to form persulfide. Covered by Damien earlier, we know how to balance this equation. First, balance the number of sulfur atoms, then balance the charge. Now, relating to the individual sulfur atoms on these species, sulfide has a -2 charge, but the persulfide has a single negative charge. How does this relate to the spectra? Well, following the 3-volt series, we notice 2 pre-edge features. This is the persulfide, and here is the sulfide. Linking this back to the ionization, we stated that voltage affects the Zane spectra. Well, this is a perfect example. If we look at the pristine series, which relates to the species in its original form, there is no rising edge for persulfide. Quoted from the article, upon discharge of lithium iron sulfide, sulfur X-ray absorption spectra's features closely resemble those in pristine material. The strong pre-edge feature at 2472 electron volts, which is here, indicative of persulfide, is no longer present, suggesting that sulfide oxidation to persulfide is reversible. Meaning, persulfide is most likely reduced back into sulfide after being discharged from 3 volts. Relating to context in a cathode, a manufacturer needs to know how their cell's material acts when it's charged. In this instance, it's formation of persulfide bonds. Overall, we wouldn't be able to cover this topic of analysis without Zanes determining its oxidation number.
That's it. Thank you for watching. We hope you enjoyed our presentation. It's bye from me and bye from everyone else.